Good evening, everybody. As the discussion of time period of pendulum is going on. In this article, we had discussed linear pendulum and as well as non-linear pendulum. So, it will not be good if we do not discuss the time period of physical or compound pendulum and torsional pendulum. And therefore, today in this class, we are going to discuss the time period of physical or compound pendulum. Let us see. The time period of physical or compound pendulum. Firstly, we try to know in which way the physical pendulum oscillate. However, we have to perform the oscillation when angular amplitude is very small. Under this supposition, we are going to find the time period of physical or compound pendulum. Let us see the physical pendulum. Let us see here. This is supposed to be a physical pendulum. However, oscillation is small, so angular amplitude is very small. We cannot say a smallness of the degree, 1 degree or 2 degree, 3, 4 degree, but it is very small. So, but for the sake of convenience, for the visibility, we have decided say 30 to 45 degree. Let us see from here. Again, say we assign it say at 60 degree and then let it go from this position so what we observe here? Here is the point of suspension. There is the body. But to understand the realistic situation, so we have to assume that point of suspension inside the body. However, it is difficult to understand from here, but we may understand like that here. Say in the second, look at here. Support is a uniform rod. Here is the small hole and then aside it like that. This is the realistic situation. They hard to perceive it, but the case like that here. This is the physical pendulum or the compound pendulum. Look at here. So this is the, however, very small and very raw way to demonstrate the physical pendulum, but it will give you insight of the physical pendulum. Now look at the book. So suppose here is a body of any geometrical shape. Suppose here is a small hole from which the body is hanged, and about this point is known as point of suspension, about which this body oscillate. However, oscillation is very, very small. That is, angular amplitude is very, very small. So here's the body, say here just below it, say at a distance of L from the point of suspension, the center of mass of the body or center of gravity exists. However, there is a small difference between center of mass position and center of gravity positions. So we will see in the class of gravitation. Surely we will discuss the difference, however, slight difference between these two, but there is a difference. So it is not worthy to discuss here right now. The center of mass, or as good as, majority of cases, as good as center of gravity. So here, so it is this body has been displaced, say by a small angle theta. However, just we are going to depict here a large angle, seems to be a large angle, to clarify the situation well. So here, so the body just takes the shape like that. Center of mass comes here, say the angle, say theta now, looks very large, but it is very, very small. And then we let it go from this position, then it starts oscillating. So comes leftward from this position, comes to the mean position. So mean position is here at the vertical. This is the vertical line. So which axis about which the body oscillates? The axis is horizontal. Look at here. Body oscillates in a vertical plane about a horizontal axis. Say this is O, and suppose this is the axis, say O prime. This is the horizontal axis, mind you. This is horizontal axis. So here, this angle, customarily we call it minus theta naught. Now again, as we had assumed in case of linear or non-linear pendulum, there is no dissipative forces acting on the system. So, if it starts oscillating, then it continues for forever. However, in the realistic situation, it did not occur like this, but when we try to establish a physical relation, or we try to find the physical formula, mathematical formula, then we have to consider the imaginary cases. You might say imaginary, it is the real situation, we cannot say imaginary, but we have to imagine, we have to assume like that. That is why, in that sense, we call it here imaginary, or we assume something else here. But one thing is understood, this pendulum is oscillating in uniform gravitational field. However, no way to say the gravitational field is uniform, either magnitude wise or direction wise. So Earth is oscillating. But one thing I want to clear here, the experiment is performing near the surface of the Earth. So we also assume that this physical pendulum oscillating near the surface of the Earth. It may oscillate near any celestial bodies, But right now, we consider it oscillates near the surface of the earth. That is right. So uniform gravitational field we have to assume it. Now, look at the forces acting on this pendulum. So obvious, force of gravity, same here. During the course of motion, the to and fro motion or the back and forth motion is taking place. So this force of gravity, whether the bob is there, is present, no matters. The bob is here, so we call it here bob, because we have been called it in case of a simple pendulum, linear or non-linear. So here we have to say the body, whole body, like that of bob, in fact. So body now comes somewhere at angle theta, so still mg is vertical now. No matters where the body is, mg is everywhere at any point in its path is vertically down. So this is the very major assumption on which the time period we are going to find. Now, is there any other forces acting in the system apart from what the medium or like that? No friction, no air resistance like that. No any other class of the dissipative forces acting in the system. Yes, there is a force. The point at which the body hangs, the points about which the body oscillates, that's the point of suspension. Because the body may be hanged by some other means. So that other means exert forces on this body, call it here physical pendulum or compound pendulum. But the action of all these forces, why we call it all these forces? Because the forces acting in different directions might, here agency is only one about which this body hangs. So it may act in from different directions. That is why I am calling like that. But all the forces passing through that point of oscillations. So that the force is there. Another force is force of gravity. Force is there. Of course, there is a force. But we are going to take here torque of all these forces. So torque of all these forces acting at the point of suspension turns out to be zero. Why zero? Because lever arm or moment arm is zero. So only we have left with the force of gravity. So we consider the body say at an angle theta from the vertical, at an angle theta from the vertical. So here this is the theta now. Look at here from the vertical. Angle has been measured from the vertical theta. So the force of all the forces acting at the suspension point by the material, the body hangs. So torque of all these forces comes out to be zero. So here 0 plus the torque of the uniform gravitational field mg. So R cross mg. So as we all know, the very basic formula of torque is R cross F. So what is R? Look at here, from the suspension point to the body, center of mass. This is considered as a radius vector. So magnitude of R. So magnitude of R means the distance between the point of suspension and the center of mass. We have already taken L, a small n. So this is a small n. Magnitude of force of gravity, that's the mg. And the sine of the angle between them, say it is turns out to be sine theta. Sine theta here. And the magnitude of the unit vector is, we all know, 1. No unit at all. But one more thing I have to mention here, as we have been mentioned in all the classes of the time period of the pendulum. So as the block has been decided and then leave it at any position, whatever the angle it puts, you may adjust yourself. Then it comes towards the position from where the body has been assigned, that is towards the vertical, because the body has been displaced away from the vertical. Once we have left it, then it tries to come towards the vertical. So that is why torque is restoring in nature. So put here minus sign. Minus sign only says the torque is restoring in nature. As we all know, in most of the cases, but not in all of the cases, net torque must be equal to I, that the moment of inertia about the same point of suspension, and alpha about the same point of suspension, that is called I alpha. Mind you, it is not the case of always. So here this is equal to, say this suspension point is O, so this is the IO alpha. From here we are able to find alpha. So alpha comes out to be minus mgl sine theta over I naught. So here minus mgl sine theta I naught. Look at here, I naught. What is I naught? The moment of inertia of this body about the point of suspension. So we may apply here parallel axis theorem. So here is the axis, here is the center of mass. You can see anywhere it becomes parallel because vertical plane and the horizontal axis. Horizontal axis always perpendicular to the vertical plane. So this is ICM plus total mass of the body multiplied by the distance from the point of suspension, that is from the axis, perpendicular distance in fact. Well, we call it distance, we always mean perpendicular. If we have to say oblique distance, then we have to mention in which way. So here ICM plus as we have been assumed earlier, oscillation is very small, then we may write here sine theta is as good as theta. So here under the assumption sine theta is as good as theta. Now we observe here alpha is equal to minus mgl over ICM plus ml square into theta. Now, as from simple harmonic motion, this is the angular SHM. So, the constant, this is taken as angular frequency squared. So this implies here omega square is equal to mgl over ICM ml square. So from here we find the positive square root because omega will never be negative. So it comes out to be square root of mgl over ICM plus ml square. Now we know time period is 2 pi over omega. This comes out to be square root of ICM plus ml square over mgm. You may write ICM plus ml square as the moment of inertia of this body about the point of suspension or the axis O prime, which is horizontal, and the body is oscillating in vertical plane. So you may write like this: time period is equal to 2 pi over 2 pi square root over 2 pi square root IO over mgm. That the time period of the physical pendulum under very small oscillation comes out to be time period is equal to square root of ICM plus ml square over mgm, or you may write like that: ICM plus ml square is as good as moment of inertia about the point of suspension, or you may call it about an axis passing through point of suspension, which is here in this case horizontal, perpendicular to the vertical plane in which the body oscillates. However, oscillation is very small. So the time period 2 pi under root I naught over mg. That's the case here. Now, so we have to take certain problems to understand in which way this simple formula behaves. So we take now the problem number 1. Question number 1. Or uniform rod of mass small m and length small l is hanged from one of its end by making a small hole, and it performs a small oscillation. Now we have to find time period of a small oscillation. Time period of small oscillation. That's the very simplest formula, because just we want to know how we apply the formula what we have been derived. So look at here. So just I have told you in the many places that firstly we have to depict the physical situations. So depiction is essential to do the problem easily. So we make a rod here. So solution of this problem. One thing I want to share with you, as I have been discussed the physical pendulum. Now then I am going to take a problem. So once you are learning the things by my YouTube channel, then pause for a while. Do the same problem by yourself. Firstly, if the problem has been solved or may not be solved, in both the cases, then try to see the solution what I am here providing to you. That's my suggestion. And rest all depends on your convenience. So here, take a rod, say this mass m, length L. So here is the small hole about which this oscillates. Oscillation is very, very small. So like that. So I'm showing for your convenience. I'm not going to write anything here because right now we know the formula. So just we are going to use the formula, and you are also going to use the formula in your examination hall. Whatever the examination you are going to face, competitive or academic, competition at all. So this is say theta naught, and say this is minus theta naught. Just have been depicted as just we did everything regarding this physical pendulum. So only duty of is that we have to find the distance between point of suspension and the center of mass or center of gravity of the physical pendulum. Here the physical pendulum in the forms of a uniform rod. So find this length. So we all know this length is L by 2. Okay. Or just use the formula. What I am saying here, just use the formula. Just use the formula. So it means you are going to be a formula based? No way. It is not my intention to guide in the manner you are formula based. No, it is not so. Because right now we have been discussed. That is why I am saying. So you have to use the formula only by knowing just I am going to use the formula for the particular purpose. And that is correct too. So here the time period, we all know 2 pi square root of ICM. Here the ICM, rod center of mass, and axis passing through center of mass of the rod, or the center of gravity of the rod, or the center of the rod. About an axis perpendicular to the rod. Mind you here, perpendicular to the rod. So we all know it is ml square over 12. And then treat it as a point mass of the rod, center of mass. What is center of mass? Behave or concentrate all the masses at the center and behave as a point mass. So this point mass, distance from suspension point is L by 2. So here m L by 2 whole square over mgl. That L and this L different because this L is the length of the rod and that L is the, what in the formula? Distance of center of mass from the point of suspension. So here is mgl over 2. Now we have to work it out. We have to cancel some. So here m is not 0 and defined as well, so it is comes out cancelled. Now the L by 2, yes, L by 2 on the same manner. So L by 2 has been cancelled here. So this becomes 6. Now this is 2 pi square root of L over 6 plus L over 2. So make like that here, 3 upon 3. So this comes out to be G is the square root of 2 pi square root of 314 4 by 6 4L over 6G. You may take 2 inside or you may not take 2 outside or may not. So we have to write the answer in the form what you want. Okay, where 4 is in from 4 which is taken out, then 4 pi under root L over 6G. So we write like this here, time period. So the 4 pi square root of L over 6G. Now the next problem. Problem number 2. In the above problem, if point of suspension is not known, we want to find distance between point of suspension and center of mass of the rod such that time period is minimum, such that the time period is minimum, such that the time period is minimum, and also find this minimum time period, this minimum time period. Again, we want to find what the distance between point of suspension and the center of mass of the rod, for which time period is minimum, for which time period is, and also we have to find this time period as well. So again we have to depict the situation. Depiction is same as before in the previous problem, but little bit we have to depict. It will give us what the insight of the problem. So make it here, uniform rod, mass and length. So here the center of mass. We have to search the point of suspension. So point of suspension might be above the, not below one. If the below one, then it will turn, so it cannot be oscillate like that. So that is why, say somewhere here, here is the point of suspension, and this distance, say x, about which this oscillates. So like that, just I'm going to make for depiction like that here. this say this is plus theta naught and this is minus theta naught. We have to pick up this rod at somehow, somewhere else like that. Say at theta. Say at theta here. So we are not going to do what we did for finding the formula of physical pendulum. Just we are going to use the formula with care. Otherwise, we do mistake. So it's a very simple situation. What is the time period formula? We all know 2 pi square root of ICM. We all know ml square over 12 plus mx square here. Why mx square? Because this time the suspension point is not at the one of the edge. That is why. Not at one of the end, in fact. Not the edge. You may call it edge because edge may like this way or that way. Here also the edge. So it is not good to say. It is to say not at one of the end, in fact. So this time it is not so. This time where the suspension point? That is the problem. So that is why the horizontal axis here again we are using parallel axis theorem. Here is the center of mass axis. Moment difference I will know ml square by 12. So treat all the masses as a point mass. Concentrate at the center. That is called center of mass. Position of center of mass. So this we have as a point mass and distance is perpendicular distance is x. That is why mx square over mg x. So here we have to find the x for which the time period is minimum. So somehow it is the problem of maxima or minima. So without squaring, we are unable to solve if we do not use first derivative concept. Then how? In which way? So we have read in class 10, if we have an algebraic expression ax square plus bx plus c and we have to find its maximum or minima. So without finding the first derivative, still we are in a position to find the maximum or minimum. Because ax square plus bx plus c taken as quadratic expression if a is not equal to 0. So if a is less than 0, if a is greater than 0, we have either maxima or minima. So that is why I have said here, so by class 10 method we are able to find the minimum t for which x comes out. But we are going to use here first derivative method. What is first derivative method? There are majority of functions. If they have maximum or minimum, then first derivative comes out to be 0. But there are too many functions. If first derivative comes out to be 0, they have neither maximum nor minimum. And in addition to that, there are too many functions have maximum or minimum if their first derivative is not 0. So not every one of the case I am going to take here in the physics class of physical pendulum. So in mathematics course, we will take after completion of the class 12 course, mathematics for higher secondary physics. then we will see too many cases of maxima or minima, but here we can find only for the first derivative test. So this function will give you x for which time period is minimum only by doing first derivative 0. So here, if we square both the sides, then it becomes easier. So taking square both the sides, t square is equal to 4 pi square ml square 12 mx square over mgx. Now we have to differentiate both the sides with respect to x. So this implies 2t dt over dx is equal to 4 pi square is constant, no matters. So here we use quotient rule. So this is whole square. So this is constant, comes out to be 0, mx square twice mx, and multiply the denominator mgx minus sign, and then we differentiate mgx, so it comes out to be mg, and now we multiply with the numerator. What is the numerator? ml square over 12 plus mx square. For maximum or minimum, but in case of majority of function, not always. For majority of functions, maxima or minima, these are the plural of maximum, plural of minimum. Maxima or minima may occur if first derivative dt over dx comes out to be 0. So after making dt by dx or putting dt by dx equal to 0, so this all turns out to be 0, and again this m after taking common, and g as well here. So write it down, twice x square minus l square over 12 plus x square is equal to 0. So this implies x square is equal to l square over 12. So this implies x is equal to plus minus l over 2 root 3. 2 root 3. Okay. So but x is a, say, distance between point of suspension and the center of mass or center of the rod. So it will never be negative. So take the positive roots. So this implies x is equal to L over 2 root 3. So this is the distance between point of suspension which we have to find, and now we found x is equal to L over 2 root 3. But one thing I want to mention here, for this value time period will be minimum, how one can say? Because we have to achieve the second derivative test. Second derivative test. But we may scale from the second derivative test in majority of physical situations. Majority of physical situations. Because oscillation is very small, means angular amplitude is very small. So the time period, as we have been learned, In case of dimensional analysis, as the simple pendulum here and the theta angular period increases, time period increases, they have been seen. So that is why the maximum correction is not arises here, because oscillation is very, very small. That is why this formula fits for that. Otherwise not. So no correction of maximum time period. So no correction here in these physical situations to go through the second derivative test. But here in majority of cases also we may scare from second derivative test. So after doing only the first derivative test, so this value give you the minimum. So here no correction of maximum, because the oscillation is very, very small. Angular time period depends upon angular amplitude. So here the angular amplitude is very, very small. So time period in correction is very, very small. So no correction of large or maximum time period. So that is why this is okay. Now put the value of x in the time period expression and find out t here. So now we put the time period t is equal to, here the expression 2 pi square root of L square over 12 plus m, what is x? L over 2 root 3. L over 2 root 3 whole square over mg, x is what? L over 2 root 3. Now we have to simplify it. So firstly m is not 0 and define as well, so cancel it out. In the same manner, one of the L here. What has been left? Look at here, 2 pi square root of, take, so a square has been cancelled from for L, but still for 2 root 3 is there. So here L over 12 plus L over 12, it also comes out to be 12. Why? For 2 root 3 here square, 2 2 is 4, root 3 3, 4 3 is 12. So here G, so 2 root 3 comes out to be in the numerator, 2 root 3. So here 2 pi under root is the L over 6. 6g, the 2 root 3, so cancel out here 2, 3. So again root 3, one of the root 3 has been cancelled inside it. So this is 2 pi square root of L over root 3 into g. This is the minimum time period. Now we are going to take the next problem. Question number 3. We positioned a physical pendulum in such a way that its center of mass or center of gravity above the suspension point. Above the suspension point, and then let it go. And when passes through a stable equilibrium position, that is lowest position, then its angular speed becomes theta naught dot and assuming uniform gravitational field, and as well no dissipative forces, no dissipative forces acting on the physical pendulum. Then find its time period. That's the problem. Problem number 3. Before getting indulged in this problem, just I want to discuss little bit about potential energy and mechanical energy conservation. We will take on this chapter, work energy and power, in the class 11 course. Then we will start right now. So, what is potential energy? Are we in a position to define potential energy? Answer is yes. We may define. Look at here. It is energy of possession or configuration or interaction. It is energy of possession or configuration or interaction. The last one is very important. Suppose you have a single particle system, then one cannot associate potential energy with it, because the single particle not able to interact with any other particles. So once there is no interaction, then there is no creation of potential energy. So at least 2-point particle system must required for potential energy. We may associate potential energy with masses or point masses or point charge particles. So if we have a single point mass or single point charge particle, so we cannot associate potential energy. So at least we require 2 point masses or 2 point charge particles. That is why this interaction is very good to understand potential energy. So one thing is that here. Next, suppose this is the surface of the earth. Surface of the earth. Now a small body, however very slowly, such that if we taken away few centimeters, it will take million years or billion years or trillion years, maybe more. So this small body of mass A takes from this position very slowly up to the height h. Then question is, what is the potential energy of this mass m? The obvious answer is mgh. mgh. Obvious answer is mgh. But this answer is absolutely wrong. Then how? Firstly, what I have said, what is the potential energy of this mass? If we are writing or we are saying mass, it means point mass. So we associate potential energy with this point mass. So I have mentioned earlier in this class, we cannot associate potential energy with a single point mass or single point charge particle. So how one can say is the potential energy of this? No way. So this is the potential energy of 2 point masses here. One point mass is small m, other point mass is earth. Look at earth is very big, spherical, almost spherical masses. But if we write the potential energy, we consider the potential energy here, so we have take earth as a point mass. So this is the potential energy of the 2 point mass system. One the point mass of the particle of mass m and the other earth. However, one part of a body has potential energy with respect to the other part of the same body, however in an advanced course. So we will take a little bit in the class 11 courses. We will focus on that. But right now, the earth is a point mass and the other point mass is there. So this is the potential energy of both. It is not the potential energy of the earth. It is not the potential energy of the point mass. It is the potential energy of the both point mass and the earth. Keep in mind. But one thing is here, still it is wrong. Why? Because we may define potential energy, but till date we have no formula to find the potential energy. What we are finding? We are finding the difference of potential energy. So this is not the potential energy. However, point mass, it is absolutely wrong. It is not the potential energy of earth, this mass system. Still, so we cannot find the potential energy of any system. Whatever it may comprises 2 point masses, 3 point masses, 4 point masses and so on. So we find difference of potential energy. So this expression comes out to be like that here. du is defined as minus f field dot here. So this mass is taken away from the earth surface and very near to the earth surface. So still we assume here uniform gravitational field. So by this expression, the formula comes out to be here at the surface of the earth, this system, point mass and earth, has potential energy, say surface, and this is, so take here say origin and up to height h. So we take here u0 and is the uh. So this side comes out to be uh minus u0. So this is equal to, this comes out to be, after putting everything, okay. So take the origin, upward is positive, like that. Too many calculation is there, so we'll see in the class 11 course. But right now it comes out to be mgh here. So this implies uh is equal to u surface plus mgh. At the surface of the earth, if we assume potential energy of this system is 0, then this becomes the potential energy of the system at height h. So uh is equal to mgh. Only then on the earth's surface it is assumed to be 0 joule. Otherwise we cannot say. So that is why this is not the potential energy of the system, point mass and the earth, but is the difference of potential energy if on the surface of the earth this system has 0 potential energy. So that is why. Now it is very clear. So customary we write uh is equal to, okay. Now, so here just I am going to erase it here. Now one thing I would like to mention here, because just I am going to use in that particular problem. So here is a trick, you may call it trick, because if not then you have to perform and we have to do the lengthy calculations to find, and then you have to proceed then now. So this is the reference level. However, very close to the earth's surface. If we go up, say up to height h, so you write here potential energy, assuming here GPE, here GPE is equal to 0 joule. This is the only assumption. We will see in the Gradation chapter. Minus GNM by R on the surface of the earth. How it comes out to be 0? No way. But potential energy, the energy of reference as well. So we may consider 0 anywhere else. However, in some cases restricted. So in case of infinite line charge distribution, we cannot assume potential energy at the infinite point, because there is a charge present, or there is a, maybe there is a line charge, line mass, their mass is present. So we have a certain exception, but in the majority of cases they assume 0 potential energy anywhere else. So here Gp is 0 joule. This is the only assumption. So if you go up above the reference level, so this potential comes out to be mgh. If we go say by the same or maybe different, say same, so here the potential comes out to be minus mgh. So in the examination or when solving the problem at your home as well, so this concept is very useful concept to use the potential energy of the system only after taking the on the surface of the earth or any reference level whatever you have taken. So 0. The 0 potential energy you may take anywhere else, but take care of the few cases only. So these are the cases. So now after this input we are able to understand this problem. So what is the problem? Yes, I am going to depict it. So here is the say of body. Suppose here is the suspension point. This is the point of suspension. Say O. Point of suspension. Point of suspension. Here is the horizontal axis. So here is the say center of mass. At what distance from the point of suspension is to be found. So here, say this is x. We have to find. Now, as we have seen, the point center of mass is above the point of suspension. So once it let it go from this position, so center of mass get lowered. Want to be get lowered. Center of mass, we always try to get the lowest position. That is why. So let it go. So it moves like that here, and then once it becomes, say this is x, so the body become like that, say here. once it crosses through the vertical, that the stable equilibrium position, the vertical. So once it crosses here, this angular speed becomes theta, theta naught, dot. So center of mass, say here, center of mass. So again this is x. Now, mechanical energy conservation. So we have a general proof of mechanical energy conservation. We are not going to indulge in that. Only we have to specify on those two positions in which we want to use the mechanical energy conservation. So this is the initial position, say position 1 is the final position, then position 2. We say the position 2. So here, ideal case of using mechanical energy conservation when there is no dissipative forces acting on the system. Frame is supposed to be inertial. The motion is only governed by the internal forces because the physical pendulum and earth are taken as a system. So the motion is governed, however the motion is only rotation here due to internal forces only. So it is ideal case of using mechanical energy conservation. But we will take on in very detail in the work energy power chapter in class 11 course. But one thing I would like to mention here, if the frame is non-inertial, however the dissipative force is acting on the system, not the general case. In the class 12 course, or it might have been in the higher courses, not written very explicitly. If the work done of all the dissipative forces, including the inertial forces, comes out to be zero, then still mechanical energy conservation is applicable. So rarely this concept has been discussed. But nowhere in the class 12 courses, whatever the textbook available for class 12 courses or 11 courses, nowhere it is mentioned. So we'll take on detail in the class 11 courses. But right now here, so this is the ideal case, this is the ideal one, no dissipative forces acting on the system. Only the motion is governed by the internal gravitational forces. So we may apply mechanical energy conservation. So E1 is equal to E2. So potential energy of the physical pendulum and earth system at position 1, at position 2, here the point of suspense is there. So we have to choose a reference potential is 0 anywhere in the universe. Anywhere in the universe. So but we have to choose the convenient path. So take here this the lowest position of the center of mass. We might take the GP at the point of suspension or maybe at the position 1, anywhere else. So we choose here GP is 0. GP is 0. GP 0. So look at here. At position 1 it means above the level. Here GP is gravitational potential is taken as 0. So here the value gives you difference values. However, we write the value, but we mean the difference value. So here E1 is equal to E2. It means here is the x, here is the x 2x, m g 2x. What is the kinetic energy of the physical pendulum? It starts motion, comes out to be 0. Earth is supposed to be 0. This is the kinetic energy of the physical pendulum, physical PP, physical pendulum. This is the kinetic energy of earth. Because in my system is the physical pendulum and the earth. This is equal to E2. The potential energy there is 0. Of what? Physical pendulum? Not. Earth? Not. The system. Pendulum, Earth system potential energy. We are taking a 2-point mass. Earth is taken as a point mass. Physical pendulum taken as a point mass. This is the 2-point mass system potential energy of the system, not of the individual one. So here is 0. Just what we have been assumed, and we have been taken reference point energy as 0. So 0 Joule. Now, what is the kinetic energy of the physical pendulum? Kinetic energy of the physical pendulum is half I-O. This is the point of suspension, and from this position, the stable equilibrium position, vertical position is theta naught. This is the representation of angular speed whole square, and the kinetic energy is still assumed to be at rest. So now we are in a comfortable zone. So we are able to find x from here. X comes out to be I naught theta naught square over 4 mg. So I naught is given in the problem. If not given, then we have to rectify the problem. Moment of inertia I naught we have to consider, otherwise how one can write moment of inertia about the point of suspension. So the x is known here. So we may be able to find I naught, because body's moment of inertia about center of mass. But things that which body it is. Hollow sphere, disc, nothing is mentioned. So how one can find ICM? However, by using the Palace's theorem, so distance x may be there. So no way to find I naught here, because body's geometrical shape is not given. As we know, sphere, hollow sphere, cylinder, like that, then okay, otherwise not. So I naught must be there in the problem, because perhaps I have missed to write the I naught. So assume in the problem I naught is already given. So x is well known. Now we use the formula of time period. So what is the formula of the time period here? The time period is equal to 2 pi under root I naught point of inertia about the point of suspension axis divided by m g x. X here is I naught theta naught dot square over 4 mg. 4 mg comes out to be here. So in the problem, I naught is not given. Why not given? Because I naught here cancelled out. So what we have been said earlier, what we are writing here, it may cause problem. And meanwhile, we feel some discrepancy in the problem. So that is why I have mentioned these things, but we have to wait till the end whether the variable not given, then really it will occur in the final answer or not. We have to wait till the end. That is why I have mentioned. So I naught here is cancelled. Look here. So mg is also here cancelled out. So this is the 2 is common here because 4 square root 2, this is the 4 pi over theta naught dot, this is the time period. So sometimes it give you discomfort that variable occurring but not given, but we have to wait till the end. So finally we have got the answer here. Time period is equal to 4 pi over theta naught. So in this way this problem has been completed. Now take the next problem. So next problem is this, question number 4. We have a uniform rod of mass small m, length small l, suspended at one of the end assuming a small oscillation now this rod is taken away from vertical by an angle theta naught, and at theta naught it is provided angular speed theta naught dot. Now find mean kinetic energy of the rod. In time interval of one time period. Of a small oscillation. Now, before indulging in this problem, we want to give you how one can find the average value of a given function. Average value of a given function. Say we had y is equal to f of x. We want to find the average value of y is equal to f of x in x1 to x2. That is, if the values of x varying from x1 to x2, then we have to find the average value of y is equal to f of x. So, average of f of x in x1 to x2 is equal to f of x dx x1 to x2 over dx x1 to x2. To understand this one, we take an example. Say the question is y is equal to f of x equal to sin x. We want to find the average value if x varies from x equal to 0 to say pi. So on the same line, average of f of x is equal to f of x dx 0 to pi over dx 0 to pi. Look at here, the average of f of x is equal to sin of x dx 0 to pi over dx 0 to pi. So which function we differentiate and get sin x, which is the minus cos x plus c, varying from 0 to pi over, this is the x plus a c prime varying from 0 to pi. Now look at here, to put the upper limit minus 1 cos pi minus 1 minus plus c, minus of that c has been cancelled out, so minus minus plus, so 0 1 2, this comes out to be 2. You are able to do that, and here is the pi, so value is 2 over pi. We did the calculation like that. So we required in this problem, here is the function of x, maybe function of y, function of z, function of time, function of anything else. So this is the way how to find the average value if function is known quite comprehensively. Let us start from the problem. So we have a uniform rod of mass ml suspension, and assuming small oscillation of this rod is taken away from vertical by an angle theta naught, and at theta naught it is provided angular speed theta naught dot over. Now find mean kinetic energy of the rod in time interval of one time period of a small oscillations. So we begins from the bottom line. So time period. So firstly, just we erase this one too. Here is the rod. Here is the point of suspension. So given a sided, here at theta naught. But thing is that the given angular speed theta naught bar at t is equal to 0. So time period quite easy. 2 pi under root ICM, we all know the center of mass of the rod, ml square over 12 plus m L by 2 whole square over mg L over 2. So how much it comes out to be? 2 pi, we did earlier 2, m is not 0 but defined, cancel out, take L by 2 cancel from here, is L by 6 over L by 2. So with the square, one of the L by 2 has been cancelled. Over G, take it here 3 like that, no harms at all. So 4 is 2 pi under root 4L over 6G. So take 2 from out, this is the 4 pi over L over 6G. This is the solution. In this interval, we have to find the mean kinetic energy. Okay. So now, before indulging in the finding the mean kinetic energy, so we take. So it has been moving that way, comes to vertical, goes away. But mind you, it is not at rest, theta naught. So theta naught thought is given angular speed. So it swings in this way greater than theta naught, because if it is the rest and let it go, then it goes either side with theta naught. So keep in mind here. So it is the angular motion. So we may treat like here. Theta is equal to theta maximum, that's the angular amplitude. So this theta naught is not the angular amplitude. Why? Because it has decided and given the angular speed. That is why. If angular speed is not given, so obviously this is the angular amplitude. Mind you. Theta m sine omega t, say delta. At t is equal to 0, theta is equal to theta naught. This implies sin delta is equal to theta 0 over theta maximum, say taken as 1. Now we differentiate it. D theta over dt comes out to be theta maximum. Sin differentiation give you cos omega t plus delta. Omega t plus delta give you omega, and delta is constant. Dt over dt is 1. So this comes out to be theta maximum into omega cos omega t plus delta. Now again use the initial condition. At t is equal to 0, d theta over dt comes out to be theta naught dot. So what is the value of this? Here is the theta naught dot is equal to theta maximum omega t is equal to 0, so it gives you cos delta. This implies cos delta is equal to, comes out to be theta naught over theta maximum omega, so it comes out to be 2. So square and adding 1 and 2, squaring and adding 1 and 2 gives you what? So there is theta 0 over theta maximum whole square plus theta 0 over theta maximum omega whole square, the sin square delta plus cos square delta comes out to be 1. So this implies, so what we are going to find theta m. So theta m comes out to be theta maximum, in fact. So theta maximum this comes out to be theta naught square 1 plus 1 over omega square root. So here theta maximum taken as positive square root because it will not be negative, taken as amplitude. Amplitude will never be negative. Now what is amplitude? It is the magnitude of maximum displacement either side of the mean position. Here the point of suspension, here the vertical. So in that way, now we have to find the mean kinetic energy. So look at from here. So firstly we want to write the kinetic energy. So what is the kinetic energy here? Half I naught d theta over dt whole square half. What is I naught? About the end rod, ml square by 3. How? ml square by 12 plus ml by 2 whole square. After adding, we will get ml square over 3. So here, ml square over 3. What is d theta by dt? Look at here. Theta maximum omega whole square cos square plus delta. Look at from here. Theta maximum square omega square cos square omega t plus delta. So this is the kinetic energy. Look at here. This kinetic energy is a function of time. Whatever the function does not matter. It is a function of some things. Here the function of time, and we have to find the average in terms of one time period. So now we are in a position to find the mean kinetic energy or average kinetic energy in the interval of one time period. So look at from here right now. So mean kinetic energy, the symbol is like that. This is 0 to time period. We will write time period finally after getting the answer. So you may write here 2 pi by omega. Omega is known. So here ml square theta maximum square omega square over 6 cos square omega t plus delta over dt 0 to 2 pi over omega. Now we have to find the value of this. So doing that, so make it here multiply and dt as well. So 2 and here is the 2. So take the constant out. ml square theta maximum square omega square over 12 and this is 2 pi over omega. So what is this? 2 cos square theta 1 plus cos 2 theta. 1 plus cos 2 theta. 1 plus cos 2 theta. Cos 2 omega t plus delta dt 0 to 2 pi over omega. Now we have to find dt. There is one dt taken out. Dt is here. So this is ml square theta maximum square omega square over 12 into 2 pi over omega. Okay, here dt becomes t. Now this is cos sine twice omega t plus delta over 2 omega plus c. Here 0 to 2 pi by omega. So upper limit minus lower limit. Upper limit minus lower limit. So here it comes out to be 2 pi omega 0 0 minus 0 2 pi omega. But what is here? If you put 2 pi by omega here in place of t, so omega has been cancelled 4 pi. Sin 4 pi by delta is give you sin delta. Put 0 here, sin in fact 2 delta, 2 is multiplied here, sin 2 delta. Put 0 here, so become delta sin 2 delta. So sin 2 delta minus sin delta, we got 2 omega is already common in both of them. So this value of this comes out to be 0. So we have left only t here, so it gives you 2 pi by omega. So here ml square theta maximum square omega square over 12 twice pi over omega, and here twice pi omega. So this cancelled out. So what we have left? We have left with average kinetic energy. Just we have to write in this way here. So average kinetic energy comes out to be what? ml square theta maximum square omega square over 12. Now we have to use the value of theta maximum square and omega square. So now let us put the value of this. So here ml square omega square over 12 theta maximum square, from here square, take square there, so theta naught square theta it is mistake here. Here it is not a theta naught, in fact this is the theta naught dot, so this is not correct. Theta naught dot, in fact we see earlier. So here theta maximum square give you theta naught square over theta naught dot square over omega square. This will theta maximum square. So put there theta naught square plus theta naught dot square over omega square. Now this is ml square over 12 omega square theta naught square. Now here ml square over 12 theta naught dot square, omega square is cancelled out. So now we had put the value of omega square. We got the average kinetic energy. That's the answer. But we want to get the answer after putting omega. So average kinetic energy is comes out to be ml square over 12 theta naught square, omega is under root 3g over 2a, or might be say under root 6g by 4a. Plus L square over 12 into theta dot. And this and L square over 12 theta square 6g over plus 7. So this comes out to be, say, one of the L non-zero but defined, cancel out. So this becomes mg L 6 to the 428 theta naught square plus L square over 12 theta naught dot. That's the final mean kinetic energy.